Thermionic emission is the thermally induced flow of charge carriers from a surface or over a potential energy barrier. This occurs because the thermal energy given to the carrier overcomes the work function of the material. The charge carriers can be electrons or ions, and in older literature are sometimes referred to as thermions. But if the emitter is connected to a battery, the charge left behind is neutralized by charge supplied by the battery as the emitted charge carriers move away from the emitter. And finally, the emitter will be in the same state as it was before emission. The classical example of thermionic emission is the emission of electrons from a hot cathode into a vacuum in a vacuum tube. The hot cathode can be a metal filament, a coated metal filament, or a separate structure of metal or carbides or borides of transition metals. Vacuum emission from metals tends to become significant only for temperatures over 1000 K. The science dealing with this phenomenon has been known as thermionics, but this name seems to be gradually falling into disuse. The term thermionic emission is now also used to refer to any thermally excited charge emission process, even when the charge is emitted from one solid-state region into another. This process is crucially important in the operation of a variety of electronic devices and can be used for electricity generation or cooling. The magnitude of the charge flow increases dramatically with increasing temperature. History. Because the electron was not identified as a separate physical particle until the 1897 work of J. Thomson, the word electron was not used when discussing experiments that took place before this date. The phenomenon was initially reported in 1873 by Frederick Guthrie in Britain. While doing work on charged objects, Guthrie discovered that a red-hot iron sphere with a negative charge would lose its charge. He also found that this did not happen if the sphere had a positive charge. Other early contributors included Johann Wilhelm Hittorf, Eugen Goldstein, and Julius Elster and Hans Friedrich Geitel. The effect was rediscovered by Thomas Edison on February 13, 1880. While trying to discover the reason for breakage of lamp filaments and uneven blackening of the bulbs in his incandescent lamps, Edison built several experimental lamp bulbs with an extra wire, metal plate, or foil inside the bulb that was separate from the filament and thus could serve as an electrode. He connected a galvanometer, a device used to measure current, to the output of the extra metal electrode. If the foil was put at a negative potential relative to the filament, there was no measurable current between the filament and the foil. When the foil was raised to a positive potential relative to the filament, there could be a significant current between the filament through the vacuum to the foil if the filament was heated sufficiently. We now know that the filament was emitting electrons, which were attracted to a positively charged foil, but not a negatively charged one. This one-way current was called the Edison Effect. He found that the current emitted by the hot filament increased rapidly with increasing voltage, and filed a patent application for a voltage-regulating device using the effect on November 15, 1883. He found that sufficient current would pass through the device to operate a telegraph sounder. This was exhibited at the International Electrical Exposition in Philadelphia in September 1884. William Preece, a British scientist, took back with him several of the Edison effect bulbs. He presented a paper on them in 1885, where he referred to thermionic emission as the Edison effect. The British physicist John Ambrose Fleming, working for the British Wireless Telegraphy Company, discovered that the Edison effect could be used to detect radio waves. Fleming went on to develop the two-element vacuum tube known as the diode, which he patented on November 16, 1904. The thermionic diode can also be configured as a device that converts a heat difference to electric power directly without moving parts. Richardson's law. Following J. Thomson's identification of the electron in 1897, the British physicist Owen Willans Richardson began work on the topic that he later called thermionic emission. From band theory, there are 1 or 2 electrons per atom in a solid that are free to move from atom to atom. This is sometimes collectively referred to as a sea of electrons. Their velocities follow a statistical distribution, rather than being uniform, and occasionally an electron will have enough velocity to exit the metal without being pulled back in. The minimum amount of energy needed for an electron to leave a surface is called the work function. The work function is characteristic of the material and for most metals is on the order of several electron volts. Thermionic currents can be increased by decreasing the work function. This often desired goal can be achieved by applying various oxide coatings to the wire. In 1901, Richardson published the results of his experiments. The current from a heated wire seemed to depend exponentially on the temperature of the wire with a mathematical form similar to the Arrhenius equation. Later, he proposed that the emission law should have the mathematical form where J is the emission current density, T is the temperature of the metal, W is the work function of the metal, K is the Boltzmann constant, and Ag is a parameter discussed next. In the period 1911 to 1930, as physical understanding of the behavior of electrons in metals increased, various theoretical expressions were put forward for Ag, by Richardson, Saul Dushman, Ralph H. Fowler, Arnold Sommerfeld and Lothar Wolfgang Nordheim. Over 60 years later, there is still no consensus amongst interested theoreticians as to what is the exact expression of Ag. But there is agreement that Ag must be written in the form where lambda r is a material-specific correction factor that is typically of order 0.5, and AO is a universal constant given by where m and minus e are the mass and charge of an electron, and h is Planck's constant. In fact, by about 1930 there was agreement that, due to the wave-like nature of electrons, some proportion ρ of the outgoing electrons would be reflected as they reached the emitter surface. So the emission current density would be reduced, and lambda r would have the value. Thus, one sometimes sees the thermionic emission equation written in the form. However, a modern theoretical treatment by Modinos assumes that the band structure of the emitting material must also be taken into account. This would introduce a second correction factor lambda b into lambda r, giving experimental values for the generalized coefficient Ag are generally of the order of magnitude of AO, but do differ significantly as between different emitting materials, and can differ as between different crystallographic faces of the same material. At least qualitatively, these experimental differences can be explained as due to differences in the value of lambda r. Considerable confusion exists in the literature of this area because many sources do not distinguish between Ag and AO, but just use the symbol A indiscriminately. Equations with and without the correction factor here denoted by lambda r are both given the same name, and a variety of names exist for these equations, including Richardson equation, Dushman's equation, Richardson-Dushman equation, and Richardson-Lauer-Dushman equation. In the literature, the elementary equation is sometimes given in circumstances where the generalized equation would be more appropriate, and this in itself can cause confusion. To avoid misunderstandings, the meaning of any alike symbol should always be explicitly defined in terms of the more fundamental quantities involved. Because of the exponential function, the current increases rapidly with temperature when kT is less than W. Schottky emission. In electron emission devices, especially electron guns, the thermionic electron emitter will be biased negative relative to its surroundings. This creates an electric field of magnitude F at the emitter surface. Without the field, the surface barrier seen by an escaping Fermi-level electron has height W equal to the local work function. The electric field lowers the surface barrier by an amount delta W, and increases the emission current. This is known as the Schottky effect or field-enhanced thermionic emission. It can be modeled by a simple modification of the Richardson equation, by replacing W by. This gives the equation where epsilon 0 is the electric constant. electron emission that takes place in the field and temperature regime where this modified equation applies is often called Schottky emission. This equation is relatively accurate for electric field strengths lower than about 108 Vm-1. For electric field strengths higher than 108 Vm-1, so-called Fowler-Nordheim tunneling begins to contribute significant emission current. In this regime, the combined effects of field-enhanced thermionic and field emission can be modeled by the Murphy-Good equation for thermofield emission. At even higher fields, FN tunneling becomes the dominant electron emission mechanism, and the emitter operates in the so-called cold field electron emission regime. Thermionic emission can also be enhanced by interaction with other forms of excitation such as light. For example, excited Cs vapors in thermionic converters form clusters of Cs Rydberg matter which yield a decrease of collector-emitting work function from 1.5 electron volts to 1.0–0.7 electron volts. Photon-enhanced thermionic emission. Photon-enhanced thermionic emission is a process developed by scientists at Stanford University that harnesses both the light and heat of the sun to generate electricity and increases the efficiency of solar power production by more than twice the current levels. The device developed for the process reaches peak efficiency above 200 degrees Celsius, while most silicon solar cells become inert after reaching 100 degrees Celsius. Such devices work best in parabolic dish collectors, which reach temperatures up to 800 degrees Celsius. Although the team used a gallium nitride semiconductor in its proof-of-concept device, it claims that the use of gallium arsenide can increase the device's efficiency to 55 to 60%, nearly triple that of existing systems, and 12 to 17% more than existing 43% multi-junction solar cells. Thermionic emission from graphene. Compared with their traditional bulk metal or semiconductor materials, graphene has many unique and excellent properties, such as atomic layer thickness, linear band structure near Dirac cone, ultra-high Fermi velocity, etc., making traditional Richardson's law derived for bulk materials invalid for graphene. Researchers from Singapore University of Technology and Design have proposed that there exists a new scaling of thermionic emission from a single-layer graphene which has been verified with an experiment. They also proposed that graphene-based vacuum thermionic energy converter has an efficiency of about 45%, with cathode temperature ranging from 700 K to 900 K, which is greatly reduced compared to the traditional thermionic converter of above 1200 K and has a promising application in recycling the waste heat from industrial processes.